Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Today we are going to do the problems on Fourier series in the arbitrary interval minus L to L. Already we have done problems on Fourier series in different intervals in the last session. Now, before going to the problems of the Fourier series, we need to learn we need to recapitulate once the formula of Fourier series. The expansion of any function in the Fourier series is given by a0 by 2 plus summation an cos nx plus bn sin nx. Here a0, an and bn are called as the Fourier coefficients. We need to find out the Fourier coefficients a0, an and bn. Now we'll see one example in the interval minus L to L. Find the Fourier series for the function f of x is equal to 1 plus x from in the interval minus 2 less than or equal to x less than or equal to 0, 0 less than or equal to x less than or equal to 2. And with the help of this, we need to deduce that n rises from 1 to infinity 1 by 2n minus 1 whole square is equal to pi square by 6. Now, before going to the problem, let us see whether this function is even or odd function. F of minus x is equal to 1 minus x in minus 2 comma 0, which is equal to f of x into 0 comma 2. Similarly, f of minus x is equal to 1 plus x in 0 comma 2, which is equal to f of x and in minus 2 comma 0. Therefore, we can say that the given function is an even function. We all know that for the even function, bn value, the Fourier coefficient bn is reduced is equal to 0. We need to find out only two Fourier coefficients, that is a0 and an values. So what is the a0 value? A0 value is nothing but 1 by L integral 0 to n 2 by L. Here we are taking the interval minus L to L. So 2 by L integral 0 to L 2 by L integral 0 to L f of x dx. F of x is nothing but here f of x is a discontinuous function at 0. So from 0 to, that is the total interval is minus 2 to 2. So we have to split up the interval. Otherwise we can do like this. That is 2 by 2. L is nothing but the interval is 2. So 2 by 2. It is 1. Integral 0 to 2 f of x dx, integral 1 minus x dx, integral of 1 is x minus integral of x is x square by 2 from 0 to 2, and which comes out to be 0. So a0 value is equal to 0. So now let's find out the an value. An is equal to 2 by 2 integral 0 to 2 f of x cos n pi x by 2 dx, and which comes out to be integral 0 to 2 1 minus x cos n pi x by 2 dx. So again I'm assuming this as f and this as g. I'm using integration by parts, which is already done in the previous section. Integral of f into g is equal to f into g1 minus f dash into g2 plus f double dash into g3. This is a unique formula which we are using for finding out the integration by parts for any product of the functions in a Fourier series. So 1 minus x is assumed it as f. F is as it is, integral of cos n pi x by 2. That is nothing but sin n pi x by 2 by the coefficient n pi by 2 minus the derivation of 1 minus x, that is minus 1, minus and the integral of sin x, that is nothing but minus cos n pi x by 2. The coefficient is n pi by 2, and 1 more n pi by 2 in the previous term. So totally it becomes n square pi square by 4 here. So now we'll apply limits. For while we are applying limits, the first term is automatically become 0 at 2 and 0. So we are left out with minus 4, minus 1 whole to the power of n by n square pi square, and minus of minus 4 by n square pi square. That is nothing but 4 by pi square n square 1 minus 1 whole to the power of n. So substituting these two values in the given function, we are going to get the Fourier expansion as 8 by pi square 1 by 1 square cos cos pi x by 2 plus 1 by 3 square cos 3 pi x by 2 plus 1 by 5 square cos 5 pi x by 2, so on. So for deduction, we will substitute x is equal to 0. If x is equal to 0, f of 0 is equal to 8 by pi square, 1 by 1 square plus 1 by 3 square plus 1 by 5 square, so on. And but if x is equal to 0, the point of discontinuity is there. So we shall have f of 0 value we need to find it out. That is f of 0 minus plus f of 0 plus by 2, which comes out to be 1. So substituting here, 1 is equal to 8 by pi square, 1 by 1 square plus 1 by 3 square plus 1 by 5 square, so on, and which comes out to be pi square by 8, which is equal to summation n rises from 1 to infinity 1 by 2n minus 1 whole square. So this is how we can find it out. The next question, I am taking again a discontinuous function f of x is equal to x in the interval 0 to l by 2 and l minus x in the interval l by 2 to l. So here the function is a sine function. For sine function we need to find it out only one Fourier coefficient, that is Bn, and both a0 and an both will become 0. Both a0 and an become 0. So we are going to get it as Bn is equal to 2 by L integral of f of x sine n pi x by L dx. This we need to substitute in the Fourier coefficient. F of x is equal to summation Bn sine n pi x by L. So here f of x is equal to x in the from 0 to L by 2. So that comes out to be 2 by L integral 0 to L by 2 x sine n pi x by L dx plus 2 by L integral L by 2 to L 1 by L minus x sine n pi x by L dx. I am using integration by parts here, integration of f into g once again. So we are going to get it as 2 by L x as it is minus cos n pi x by n pi by L minus derivation of x is 1 minus sine n pi x by L by n square pi square by L plus 2 by L minus x minus cos n pi x by L minus of minus 1 and again the integration of minus cos theta, that is sine theta, and after substituting the lower and upper limits as L by 2 and L, we are going to get the Bn value as 2 by L to L square sine n pi by 2 by n square pi square, and that we need to substitute in the Fourier expansion to get the Fourier series. And the Fourier series is given by f of x is equal to summation. Here we need to substitute a Bn value that we have got n rises from 1 to infinity Bn sine n pi x by L, that is summation n is equal to 1 to infinity 4L by n square pi square sine n pi by 2 into sine n pi x by L, and that comes out to be 4L by pi square 1 by 1 square sine pi by 2 sine pi x by L plus 0 plus 1 by 3 square sine 3 pi by 2 sine 3 pi x by L plus 0 plus 1 by 5 square sine 5 pi by 2 sine 5 pi x by L plus 0, so on, and that comes out to be 4L by pi square 1 by 1 square sine pi x by L minus 1 by 3 square sine pi x by L plus 1 by 5 square sine 5 pi x by L, so on. So this is the required expansion for the given function in the interval minus 1 to 1. So that is how we can do the problems in the Fourier series of minus 1 to 1. Throughout the unit, this is the last class of the Fourier series, last session of the Fourier series, and throughout the Fourier series we need to find out only 3 Fourier coefficients, a0, an and bn. And sometimes the function is even, sometimes the function is odd, sometimes the half range cosine series is asked, sometimes the half range sine series is asked. So based on this, a few Fourier coefficients will reduce to 0, and the remaining the Fourier coefficients we need to find it out. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.